This video provides an overview of the Bridge Scour tool in SMS, and it demonstrates how to extract the hydraulic parameters that are needed to perform a bridge scour analysis. It supports Exercise 11 of the FHWA National Highway Institute training course on two-dimensional hydraulic modeling of rivers at highway encroachments, course number 135095. This video is intended to focus on how to extract 2D hydraulic model results to support bridge scour analysis and not how to compute scour. For information on how to utilize the extracted parameters in computing scour, please refer to FHWA's HEC 18 document on evaluating scour at bridges. If you are not familiar with some of the terminology we use as we discuss bridge scour analysis, please refer to the glossary in the HEC 18 document. For this exercise, we've opened an SMS project for a bridge crossing on the Middle Fort Clarks River in Kentucky. The flow runs from the left to the right, with the bridge of interest located in the center of the terrain data shown on the screen. This project includes 3D bridges that have been generated for the main bridge and relief crossings, and we can turn on these bridges by selecting the U-grid data, making all of those active. Then we can rotate the view and zoom in to take a closer look at what the bridges look like. Prior to extracting hydraulic data for a scour analysis, it is best to run several flood flow conditions in order to assess the worst case scour condition. So for this project, we can see in the Project Explorer that 4 simulations have been run already and the results have been loaded. These include the Q overtopping and incipient overtopping flow, 50-year, 100-year, and 500-year events. Now we are ready to create a new bridge scour coverage and draw the necessary reference arcs. To create a new coverage, right-click on the map data, select New Coverage, and the bridge scour type. We could use the default name of bridge scour, but for our demo, we'll change this to bridge scour EC for existing condition. The welcome screen pops up with 2 very helpful links. One to the wiki site with an explanation of the workflow steps and another wiki page with additional help information. When we exit this screen, the Bridge Scour Coverage Properties dialog opens. We'll need to enter information on this page, but for now we'll close it and come back later. For the Bridge Scour tool, we need to draw arcs to represent the contracted section, the approach section, channel center line, bank reference locations, abutment toe locations, and pier locations. The contracted section arc is the first to be drawn. Let's start by zooming in closer to the bridge location to draw the contracted section arc. It's also helpful to turn off any 3D bridges. And then we select the bridge scour coverage, make sure it's active. Select the Create Feature Arc tool, and then draw an arc from left to right looking downstream across the bridge section, generally down the center line of the embankment. The length of the arc only has to extend across the bridge opening, and it will establish the limits of the bridge scour plot that will be used in the hydraulic toolbox. The arc is generally drawn along the center line of the roadway embankment, and in some cases where the flow is still contracting through the bridge opening and we have higher velocities near the downstream face of the bridge, it may be prudent to draw the arc closer to the downstream face. But for this case, the center line approach appears to be fine. If we draw These Bridge Scour Tool arcs, in the order that I mentioned them originally and the order that I will demonstrate them, the correct type will be assigned automatically. Otherwise, there is a pull-down menu to reassign the correct type as needed. For example, if we select the contracted section arc, right-click that, and select Arc Attributes, the type is assigned as a contracted section arc. If we were to change that, we click the pull-down and we could select a different type. You can see the types that are listed are in the order, the preferred order for generating those arcs. If we use this order, the arc type will be assigned automatically. So let's leave that as the contracted section arc. Close that. And next we'll draw the approach section arc. And as we do this, we'll pan upstream slightly. It's probably helpful to declutter a few things. We'll turn off the background image, but it's also helpful to turn on the vectors. And it's also helpful to view the velocity results. So let's just start by looking at the incipient overtopping event. Select the velocity there. Now, in placing this upstream approach arc, there are two objectives. The first one is to place it upstream of the location where we first start to see overbank flow being directed or diverted towards the main channel. If we take a closer look here, you can see the velocity vectors are parallel to the floodplain, and at some point towards the bridge, they start to be redirected towards the channel. Similarly on the left bank. So a location somewhere anywhere upstream of this location would be acceptable. Now the other objective in placing this approach arc is to place it in a location where the velocities in the channel are representative generally of the lower end of the average velocities through the approach reach. Because this velocity will essentially be used to define the sediment capacity that may be delivered to the bridge. If we select an isolated area of high velocity, it would tend to overpredict the sediment delivery to the bridge, and that would underestimate the scour potential at the bridge. So as we look along the reach, we see high velocities in this bend, and the high velocities continue a little bit. But at this point, we see lower velocities in a reach here, and that would be the most appropriate location to draw the approach arc. I also prefer to place that in a location where I can cross the channel perpendicular with the arc, and so I'm going to choose this location upstream, and again make sure that the bridge scour coverage is selected. We have our Create Arc tool selected, and we draw this from left to right, looking downstream. You can have multiple points, and generally it's best to draw this perpendicular to the flow, but it's not absolutely necessary because the flow direction is taken into account in the computations. And then extend the arc across the entire width of flow that's tributary to that bridge. Double click that to end it. Now the third arc is a channel centerline arc drawn from the upstream to downstream, generally along the center of the channel, and it only has to be long enough to capture both the approach section and the contracted section. You can end that a short distance downstream. The next four arcs are the bank location arcs at the approach section and the contracted section. The order that they are drawn and the direction they're drawn, the length of the arc, and alignment do not matter. It's only the intersection of these arcs with the approach and contracted sections that is used to compute the main channel width and extract the hydraulic parameters. placing these arcs, it can be helpful to turn off the velocity vectors. And then also we can go back to viewing the terrain. And it's also helpful to view the terrain with linear contours. Start with the approach section. As we zoom in on the approach section, we have two options. The recommended option to place bank arcs is at the toe of the slope. And if you can look at these, as we see these linear contours defining both banks, there's a fairly distinct toe of slope down here that we will place the first bank arc and the second bank arc. Now, we could alternatively place these arcs at the top of banks on either side, and that's okay as long as we use a consistent approach between the approach section and the contracted section. But again, we prefer using the toe of slope as that's typically a better definition of the portion of the channel that's transporting sediment. So those are the first two bank arcs. And one other thing that is helpful is to turn on, in display options, turn on the legend for the map coverage. And as we place arcs, you'll see the legend identifies the type of bank arc. So it's easier to confirm that we have the correct type without having to select each arc. So we can see the dashed brown line corresponds to these bank arcs. Now pan downstream to the contracted section arc, and we'll do the same thing. Now we want to place these bank arcs at the toe of the slopes for the main channel. It's a little more challenging for this case since we have a secondary channel, but we can assume that most of the sediment transport will be in the main channel, and so we're going to ignore that secondary channel. So again, on this bank, we can see a fairly distinct toe of slope here, and approximately here. That's, again, our 4 bank arcs. One thing that is important to note is that when the Bridge Scour tool extracts hydraulic parameters, the data is automatically adjusted to reflect the skew of the bridge relative to the approach flow, as well as the skew of the piers. The next 2 arcs are the abutment toe arcs. And as with the bank station arcs, the length, the alignment, and direction do not matter. It is only the intersections with the contracted section arc that define the main channel and overbank regions. So for this case, we'll select locations on the right bank for the abutment arc and on the left bank. Now we do want to ensure that those arcs are actually in the flow, otherwise abutment scour will not be computed. So we can turn on one of the solutions, we can go back to the velocity, right? And again, for that lower flow, those arcs are wet. In many cases, clearly identifying the abutment toe location can be difficult, but the good news is that the location is not critical. The Bridge Scour tool in SMS is only set up to use the NCHRP method, abutment scour method described in HEC 18. And that method has a scour condition A or a scour condition B. Scour condition A uses main channel averaged hydraulics to compute the maximum flow depth, so the maximum flow depth with abutment scour at either abutment. And this assumes that the main channel can migrate across the entire width of the bridge opening. And so again, that's abutment scour condition A. If that were not the case, if the main channel was not likely to encounter an abutment over the life of the bridge, we would use scour condition B. We will identify that later in the Bridge Scour Properties dialog in SMS. But again, it's important to note that the placement of these arcs is not critical. Okay? So again, the total flow depth with abutment scour is being computed. If we place the arc higher in the slope, right, the resultant scour at that location will be greater. The lowest elevation will be the same. Whereas if we place that arc farther down the slope, right, the local flow depth will be greater and the computed scour will be less. But again, the total scour elevation would be the same. There's one more thing to note for the bridge abutment toe arcs, and that is that if we select each arc, we have the option to set the type of abutment. Okay, both of these cases are spill-through abutments, but if they were not, if they were vertical abutments or vertical abutments with wing walls, we could select those options. We would do that for both abutments. But the default is the sloping or the spill-through abutment. Okay, so finally, we'll draw the pier arcs. For these arcs, the alignment and length are important, okay, but the direction that the arc is drawn is not. So we can draw these arcs either in upstream to downstream or downstream to upstream. Generally represent the center line of the pier. Okay, for this case, we have wall piers, but for the case that we might have cylindrical piers or a single pier or columns, we recommend drawing this arc from the upstream face of the upper column to the downstream face of the downstream column. We can select both arcs. This is unique to for the piers. We can select both arcs, right-click, and edit those attributes. There we would set the pier shape. Okay, for this case, we have a square nose. And the bed condition we would select. For this case, we'll select plain bed. We have to enter the pier width. Now this is assuming the pier width for all the selected piers is the same. And we can also override the pier length. So this pier length here is set right now as the average of the two arcs that we drew. I'm going to change that to 40. And then we have to set the reference locations. And again, if there is potential for the main channel hydraulics to impact these piers over the life of the bridge, we would definitely use the main channel as the reference. If for cases there are piers that are set back and we're confident that the main channel flow will not impact those piers over the life of the bridge, we could use the local stream bed elevation and the local hydraulics. But for this case, we'll assume the main channel hydraulics are in play for both. We can also override the local angle of attack. So if we were comparing a observed scour hole with a measured event, we would use the actual computed angle of attack. But for design purposes, it would be more appropriate to override this angle and enter an angle, say, between 10 to 20 degrees for design purposes, knowing that that angle of attack may change over the life of the bridge. And then this pier bottom elevation is used only for plotting purposes to show that the lengths, where the piers extend to. If we know that pile tip lengths, we can enter that, or at least we want to enter a low elevation to show the piers in the plot. Now that we have placed all of the required arcs, the Bridge Scour tool is ready to extract the averaged hydraulic parameters for this case. Now, if you recall, we looked only at the overtopping case, but generally this Bridge Scour coverage would be appropriate for each of these cases, unless there were significant differences in flow patterns and hydraulics between each of these events. But in most cases, a single Bridge Scour coverage would be appropriate for a range of flood flows. Before we proceed with the main bridge, let's take a quick look at how we would lay out the bridge scour coverage for computing scour at the relief bridge. It's essentially the same process, repeated using a new bridge scour coverage. Now for this demo, we've already completed the steps for the relief bridge, so we'll turn on the other coverage. And if you'll note, we've got a bridge scour folder that already has the relief bridge. We can turn that on, but we can also grab our new coverage and drag and drop that under that bridge scour folder. If we take a closer look at the bridge scour relief bridge coverage, we can note that all of the same arcs were used. The contracted section arc, we have the approach section arc. We can turn on the velocity vectors to observe the placement there. Now the one thing that's can be different is that for relief structures, right, since the overbanks are predominantly vegetated and it's uncommon to have a consistent supply of sediment transported in the overbanks, most cases for relief structures are a clear water scour case. So in that case, the only parameter that is used from the approach section is the average unit discharge upstream. And oftentimes there's not a well-defined main channel upstream of a relief structure. And so in this case, we've placed those bank arcs near the outer edge of the flow that is tributary to that relief section. And again, that's simply going to be used to compute an average unit discharge for computing abutment scour at the relief bridge. Okay, now that we've taken a brief look at our scour at the relief bridge, let's go ahead and go back to the main bridge just by selecting that coverage, right-clicking, and selecting Bridge Scour Properties. We will work through this dialog from top to bottom, one section at a time, starting with Define Soil Gradation. Here we can enter the number of data points that we wish to use in the gradation. Oftentimes we may have a gradation already set up in a spreadsheet that we can copy and paste here after specifying the number of points. However, for the current scour analysis, we were only provided 1 point, the D50 of 0.0047, which I believe is approximately 1.4 millimeters, and a percent passing of 50%. You can see our scale ranges from 0 to 1, so 50% would be 0.5. When we're using the HEC 18 methodology, the D50 is really the minimum that we need. And so we at least need to enter this 1 point. But for some other purposes, it may be helpful to have more gradation information. Okay? But most importantly, it is important to have a gradation that's representative of the channel bed material. Mainly at the approach section, so we can determine whether there is live bed or clear water scour. But also, if the gradation is different at the contracted section, it's important that we have that gradation information available as well, both for surface material as well as any subsurface layers that exist if potential scour would exceed that upper layer. But for this tool, currently there's only one gradation option. So we recommend entering the gradation for the bed material at the approach section, and if adjustments are needed for the contracted section, we can take care of those in the hydraulic toolbox. In the next pull down, we see the mesh type. And this defines basically which terrain data set is used for extracting the geometry and which will be used as reference point for computing the hydraulic parameters. In this case, we only have one mesh, so it's easy. We'll select the existing condition mesh. And next we see this in the scenarios window. It's currently blank, but we can add scenarios by clicking the plus symbol and then selecting the folder for each of the simulations that have been run. And as we do this, it's going to populate a scenario name, and we recommend deleting the SRH2D in parentheses and keeping this name fairly simple, as this is a label that will be used later in the tables and the plots. When we select that folder, all of the data sets are automatically populated for the last time step in that simulation. If we wished to use a different time step, simply select on the time step and select other time steps if they're available. In this case, we just ran a steady state simulation with output at the last time step. So we can close this and then click on the plus symbol and repeat the process for the remaining 3 data sets. Just below the scenarios window, you can see there are additional buttons for options, critical velocity, and view values. If we wish to go back and change settings for each of the scenarios, simply select on the scenario, click on options, and we can change either the scenario name or we can change the time step if we so choose. Also, for each selected scenario, if we click on the critical velocity, it will show us the computed critical velocity at the approach section for that scenario. Also, for each scenario, before we export values, we can view them by clicking on the view values and then scrolling through all of the data and reviewing main channel hydraulics. You can see we've got main channel at the approach section. We've got overbank hydraulics at the approach section. We've got contracted section hydraulics both at the main channel, overbanks. Again, if we scroll through, we've got all of the abutment hydraulics that are extracted, as well as the piers. We'd like to highlight here that for each pier, it does generate the local approach depth and velocity upstream of each pier. However, the values that are exported to the hydraulic toolbox are the approach velocity and depth at the highest unit discharge approaching the bridge. Okay, so this would be a value upstream of the bridge, and this accounts for the possibility of that channel migrating across the entire width of the opening, or at least moving and possibly encountering each pier with those maximum hydraulic conditions. If we wish to use those local velocities and depths, we would have to manually record those and enter those into the hydraulic toolbox. Okay, below the scenarios window, we can see that there's a bridge deck entry option. This is optional. If we do have a 3D bridge, we can select a 3D bridge. In this case, just the main bridge. But again, if we didn't have this, I guess it's just for plotting purposes, or we can later on enter bridge information in the hydraulic toolbox manually if we wish to add that to the plots. Okay. But otherwise, with the 3D bridge selected, the 3D bridge geometry and the channel bed geometry are exported automatically to the hydraulic toolbox. Below the bridge deck entry, we have an option to enter an offset for pier hydraulics. The default is set at 0, which in that case, if it's set at 0, the pier length is used as the offset upstream of the contracted section. Okay. We found that this has generally been a good reference point, but we do want to look back to later on to make sure that this is adequate. So for this case, remember our pier lengths were 40 feet. So this is going to reference a section 40 feet upstream of the contracted section arc. Below that, we have a model specifications entry. For the contraction scour variable extraction approach, we currently only have one method, and so leave that at the bank width ratio option. Then, as I mentioned earlier, we do have to select the NCHRP abutment scour condition for each abutment. So the scour condition A will apply main channel hydraulics when computing abutment scour, and scour condition B will use those overbank averaged hydraulics for computing abutment scour. In many cases, these may be the same, but if you've got a wide floodplain in one overbank and the channel is not likely to migrate, you may have a scour condition B potential there. Next, we enter an output file name and specified directory. Now we will export the hydraulic toolbox file by clicking on the export button and waiting for successful export notification. And then by clicking the Launch Hydraulic Toolbox option, this will open the exported file into the correct version of the hydraulic toolbox, even if you do not have the latest version installed on your computer. It is automatically included with the SMS installation to avoid version issues. But before we do that, we can see that the arcs generated for the Pier Scour variables are shown in the Bridge Scour coverage for review, but they can be deleted if desired by clicking on the Delete Generated Arcs option. So if we close this window, we can turn off the mesh, we can zoom in, you can see this dashed arc is the reference location for extracting the Pier Scour variables. We can also see the arcs that are used to compute the approach flow direction. Okay, now we're not going to go into a detailed description of the hydraulic toolbox, but at least I'd like to show you enough to give you an overview of what it looks like. So if we go back to our Bridge Scour property dialog, click on Launch Hydraulic Toolbox, it automatically opens up the data that we exported. So double click on that. We can see at the top here just a couple things. It does show that we have 4 scenarios worth of data that have been exported. There's a section on contraction scour. There's a section on the bridge geometry, section on pier scour, as well as abutment scour. I definitely recommend you go through each one of those to make sure the data was imported correctly from the Bridge Scour tool in SMS. I wanted to highlight just a couple things. Under contraction scour, for instance, let's look at the 100-year event. And under the contraction scour for the main channel, you see there's several options here. Clear water or live bed is the default. We can also select clear water and live bed. It'll compute both. In this case, you see it's computing a clear water case. And for that, the data that's been imported, the scour depth is around 12.8 feet. Again, all of the data that's in these white boxes has been auto-populated from the Bridge Scour tool. It's important just to glance through that, make sure everything looks correct. And then in probably about 95% of the data entry that's required for the toolbox is exported from the Bridge Scour tool. There's still a few remaining items that have still yet to be integrated. I want to highlight one of those. So, well, first of all, let me go back and I want to highlight the Bridge Scour summary table. So once we've reviewed all of the scour for each of the components, there's a Bridge Scour summary table that will give a summary for each event and for each scour component and provide elevations. We can then look at a cross-section, and for now, let's select just the 100-year event. Plot that, so it'll show the resulting total scour. You can see the contraction scour, the pier scour, and the abutment scour plots, as well as the water surface. You can see the water surface is below the low chord of the bridge, so this is not a pressure flow condition. But if we were now to look at the 500-year event and plot that, it does show that the water surface is above the low chord. So this is potentially getting into a pressure flow condition, and we need to enter the appropriate values for computing pressure scour. And those are some of the variables that are currently not exported from the Bridge Scour tool. So let's take a closer look at that. So under the contraction scour parameters, there's a pull down. We can go to pressure flow, and you'll notice that there's zeros for two values: the vertical size of the bridge open prior to scour, the deck thickness, which we would need to know from the bridge plans. And then there's also another value we need to enter. It might populate with something, but we need to correct this value with the depth of flow prior to scour at the upstream bridge face. I'm going to show you, I'm going to go back to the SMS project and show you how to extract those variables. Turn on the mesh. Let's turn on the 500-year water surface solution. Let's go ahead and turn off our bridge scour coverage. You can see at the bridge, there's definitely a drop in water surface through the bridge opening. So for that, the depth upstream at the upstream face, we want to be sure to use the water surface elevation upstream of the bridge prior to the drawdown that occurs at the upstream face. We'll use that water surface elevation relative to the average channel invert at the face of the bridge to compute the approach depth. And then the opening at the bridge face would be the low chord, the average low chord at the bridge minus the average channel bed elevation. And so those are the two main things from the results that we need to export from the solution manually, as well as the bridge deck thickness. Okay, so this concludes our demonstration for setting up a bridge scour coverage in SMS for extracting the hydraulic parameters that can be used to compute scour in the FHWA hydraulic toolbox. To obtain a copy of the hydraulic toolbox and additional training on its use, you can do a web search on the NHI hydraulic toolbox. And you can also do an additional search on FHWA Bridge Scour Workshop that will connect you with further training on using 2D hydraulic model results for computing bridge scour. Good luck computing scour.